Welcome to Athletes of the Reef podcast, where we explore the fascinating world of scientific research and make it accessible to everyone. I'm your host, Alex Morgan. Today, we're diving into a biological mystery that challenges everything we thought we knew about the cost of making babies, at least if you're a shark. Usually, reproduction is the most expensive thing an animal can do. It requires energy, resources, and a massive metabolic toll. But what if I told you there's a shark that might be doing it for free? To unpack this, I'm thrilled to be joined by Dr. Jodie Rummer, professor of marine biology at James Cook University and the head of the Physioshark research program. Jodie, welcome to the show. It is an absolute privilege to have you here.
It's wonderful to be here, Alex. Indeed, it is always a pleasure to talk about the athletes of the reef, especially when they defy our expectations so completely.
I want to start with the stakes here. I think most people, whether they are parents or not, understand that reproduction is exhausting. I mean, biologically speaking, it's supposed to be a massive energy drain, right?
Absolutely. If you look at the fundamental laws of biology, reproduction is the ultimate investment. You are literally building new life from scratch. In vertebrates, fish, reptiles, birds, humans, we typically see significant shifts in metabolism. You have to synthesize yolk, build tissues, and in the case of egg layers, construct a protective shell. All of that costs ATP, it costs energy. Historically, we have assumed that for chondrichthyans, that's the class containing sharks, rays, skates, and chimeras, this process must be incredibly costly because they have such slow generation times and invest so much in each offspring.
Right. Sharks aren't exactly like goldfish spawning thousands of tiny eggs. They put a lot of work into a few kids.
Exactly. They are slow growing, late to mature, and have low fecundity. So the assumption has always been high cost. But the problem is, nobody had ever successfully measured the direct metabolic cost of this process in a shark in real time. We had estimates from bomb calorimetry, basically burning tissue to see how much energy is in it, but we didn't have the live data.
So you decided to put sharks on a treadmill while they were pregnant.
Not a treadmill per se, but a metabolic chamber. This is really the heart of the paper we published recently in Biology Open, titled Assessing the Metabolic and Physiological Costs of Oviparity in the Epaulette Shark. This work was actually led by Dr. Carolyn Wheeler, who was my PhD student at the time. She's brilliant. We co-supervised this work with Dr. Cynthia Auruch and Dr. John Mandelman. Carolyn really drove this project, spending hours monitoring these animals.
So walk me through the setup. You're studying the epaulette shark. Why this specific shark?
The epaulette shark, Hemicillium ocellatum, is a fantastic model species. They are what we call an oviparous carpet shark. They lay eggs, but uniquely, they are a single oviparity species. They have two uteri, and they produce one egg case per uterus at a time. The whole process is incredibly fast. It only takes about 2 weeks per cycle. This makes them perfect for the lab because we can track the entire process from the start of the egg formation to the moment they drop the egg case.
Okay, so you have these sharks in the lab. How do you measure how much energy they are using to build an egg?
We use respirometry. We measure their oxygen uptake rates, or MO2. Oxygen consumption is a direct proxy for metabolic rate. The more oxygen you burn, the more energy you are using. We tracked 5 female sharks over a period from March 2020 to January 2022. We measured them before they started making the egg case, the pre-encapsulation phase, then during the encapsulation phase, which is when they are physically secreting that tough, leathery shell around the egg, and finally post-oviposition, right after they laid the egg.
And the expectation was what? A massive spike in oxygen use during the building phase?
Indeed, that is exactly what we hypothesized. We expected that during encapsulation, when the shark's body is synthesizing this complex keratin collagen structure, their resting metabolic rate would shoot up. Then, after they laid the egg, we expected it to drop back down. It makes sense, doesn't it? It's hard work.
It sounds like common sense. So, what did the data say?
The data completely flatlined.
Wait, what?
Flat, no significant change. We looked at the metabolic rate across the entire 19-day cycle, whether they were just hanging out or actively building an egg case or just finished laying it. Their oxygen consumption remained statistically the same.
So making a baby, or an egg case, cost them zero extra energy? How is that physically possible? That sounds like violating the laws of thermodynamics.
I know, it was surprising to us too. Lewin, my husband, would probably look at this and say, "See, I told you it wasn't that hard," which is exactly why he isn't allowed in the lab. But seriously, it challenges our fundamental assumptions. We also looked at blood parameters, hematocrit and hemoglobin, and reproductive hormones like testosterone, estradiol, and progesterone. Aside from a small peak in testosterone early in the cycle, which likely kickstarts the ovulation process, everything was remarkably stable.
Okay, help me understand this. If I'm building a house, I need to buy bricks. I need to pay workers. I can't build a house for the same price as sitting on my couch. How are these sharks building an egg for free?
That is the million-dollar question. We have two main theories. The first involves something called the income breeding strategy. Imagine you have two ways to pay for a vacation. One is the capital strategy. You save up money in a bank account all year, your liver in the shark's case, and then you spend it all in one big burst during the holidays. That's how many seasonal breeders work. You'd see a metabolic shift as they mobilize those savings.
Okay, and the income strategy?
The income strategy is paycheck to paycheck. You don't dip into savings, you just use the cash you earn that day. In our study, the sharks were kept at a constant temperature of 25 degrees Celsius and fed regularly. In the wild, they breed seasonally when the water warms up. But in the lab, because the conditions were perfect year round, they might have transitioned to an income breeding strategy. They were taking the energy directly from their food and funneling it straight into egg production, without needing to ramp up the metabolic machinery to mobilize stored fats from the liver.
So, because they were well fed and comfortable, the cost was hidden in their daily calorie intake, rather than showing up as metabolic stress.
Precisely, it suggests a remarkable plasticity. They adapted their physiology to the available resources. If you have enough food coming in, you don't need to stress your system to reproduce. It highlights just how efficient these animals are. Healthy sharks equal healthy reefs, and part of being healthy is this ability to optimize energy use.
That makes sense. But you mentioned a second theory?
Yes, and this one is about scale. Think about a massive factory complex. That's the shark's whole body. Now imagine one tiny room in that factory is working overtime. That room is the oviducal gland, where the egg case is secreted. It is biologically very active, but relative to the size of the shark, that gland is tiny. Even if that gland is burning energy like crazy, it might not be enough to register on the whole body utility bill. The noise of the shark's general existence might drown out the signal of the egg production.
So the cost is there. It's just happening in such a localized area that the overall oxygen meter doesn't twitch.
Exactly. We call it the maintenance level. The background metabolic rate of keeping a shark alive is so much higher than the incremental cost of that small gland that we just couldn't detect the difference. This contrasts with viviparous rays, live bearing rays, where studies have shown a huge metabolic drop after they give birth. But for these egg layers, the daily cost is spread out and minimal.
I want to circle back to the hormones you mentioned. You said testosterone peaked early. Why does a female shark need a spike of testosterone to make an egg?
Great question. In the pre-encapsulation phase, we saw elevated testosterone. In many vertebrates, T is a precursor for estradiol, but in elasmobranchs, it also plays a role in stimulating ovulation and getting the reproductive tract ready. It's like the starter pistol. Once the process begins, the levels drop and stabilize. The fact that estradiol and progesterone remained consistent throughout the cycle further supports the idea that the sharks were in a steady state of production, a continuous conveyor belt of reproduction, rather than a boom and bust cycle.
This paints a picture of the Epaulette shark as this incredibly efficient biological machine. Does this give them an advantage? I mean, we talk about climate change and warming oceans constantly. If reproduction is cheap for them, does that mean they are safer?
Oh, absolutely. That is the critical context. My lab, RummerLab, focuses heavily on how climate change stressors, heat waves, acidification affect performance. If a species has a high reproductive cost, environmental stress can force them to choose survive or reproduce. They can't do both. But if the epaulette shark has this low cost, income based strategy, they might be more resilient. They can keep churning out eggs even when conditions aren't perfect, provided they have enough food.
But there's a flip side, right? You mentioned they rely on food intake for this income strategy. If climate change messes with their food supply,
Then the system could collapse. If they are relying on that constant paycheck of calories to fund the eggs and the food web gets disrupted, they don't have the capital or savings account to fall back on as easily. It's a delicate balance. But indeed, this study challenges the doom and gloom narrative that reproduction is always the first thing to shut down under stress. These sharks are tough.
it's fascinating. We usually think of biology as these strict rules. Reproduction costs X amount of energy. But nature is so much more flexible.
It is, and it shows why methods matter. If we had just looked at the caloric value of the egg, we would have said expensive. But by measuring the shark in real time, breathing and living, we see the efficiency. It's why we do what we do. And frankly, it's why I get so annoyed when people oversimplify shark behavior. They are sophisticated physiological wonders.
Before we wrap up, I have to ask. You tracked these sharks for almost 2 years. Did you name them?
We did identify them, of course. We had 5 females, but we try not to get too attached, though when you spend that many hours staring at a shark in a tank waiting for it to lay an egg, you do develop a rapport. It takes a lot of patience. Carolyn has the patience of a saint. I would have probably given up and gone for a run.
So the takeaway is, Epaulette sharks have figured out how to have kids without the exhaustion, as long as they get a steady stream of snacks.
Basically, yes, they are the ultimate budgeters of the ocean. No waste, no drama, just steady, efficient production. If only we could all function like that.
That was Dr. Jodie Rummer discussing the surprising efficiency of the Epaulette shark. It turns out, nature has found a loophole in the energy bill of life, at least for these incredible egg layers. This research, led by Dr. Carolyn Wheeler, opens up new questions about how marine life will cope with a changing world. If you enjoyed this deep dive into the physiology of the reef, make sure to follow the Athletes of the Reef podcast. Until next time, stay curious.